Hi, this is Dr. Jivikas Paul. In this session, we'll discuss a problem on shear center for the unequal I section. So determine the shear center for the I section shown in the figure. So this is an unequal I section. That means to the left side of y axis there is some dimension, to the right side there is some dimension. Means this I section is unsymmetrical about y axis and it is symmetrical about x axis. Okay, this is symmetrical about x, but unsymmetrical about y. Because left side other dimension, the right side some other dimension is there. So dimensions are shown in the figure here. Okay, and then we need to find the shear center. Okay, so this is a given figure I section. Here this is the shear flow. So whenever there is an external load on the beam, okay, there will be shear stress will be developed. Due to that shear stress resistance shear force will be developed inside a section. Due to that shear flow will be obtained. So this shear flow for the I section is in this way, from bottom like this it will go, and it will go like this, and then this is the shear flow. To the left side part of this y axis, I will take this shear force in the flange as S1, and here it has S1. To the right side S2, S2. Here it is towards this. Okay, S1, S2 are the shear forces in the flanges, top and bottom flanges, and F is a shear force, and E is the position of a shear center. That means I am assuming some point at a distance of E from the centroid O of the I section. Okay, so some E, this E I need to find shear center. Okay, right. So shear flow will be as shown in the figure due to the external force. S1 is the shear force produced on the left side part of flange, and S2 is the shear force produced in the right side part of the flange due to external load. F is the shear force. Now for equilibrium and clockwise moment about O equal to anti-clockwise moment about to O. Okay, so now clockwise moment here are S2 into perpendicular distance. What is this distance? 150 by 2. Total is 150. 150 by 2 minus this portion 20 by 2, that is 65. Okay, so S2 into 65, that is S2 into this distance, and again S2 into this one, this is same again 65, is equal to, this is clockwise moments, these both are clockwise moments, now is equal to S1 into this distance, same distance, plus S1 into again same distance anti-clockwise, and F into E. Okay, now if we solve this, we get it as F equal to this one, then E equal to S2 minus S1 135. Let it be equation number 1. Now what is S here? Shear force, that equals to shear force equal to shear stress into area. Okay, let this be equation number 2. So here shear stress formula we know, F A y bar by IB. Let this be equation number 3. Now here we need to find tau first, then we substitute here, and we'll find S1, S2, and we'll substitute here, we can find position of shear center. Now we are considering a small element of length dx at a distance of x from the tip of the flange, tip of the flange it is x. Okay, dx, dA is its area, A is the area of this shaded region. Okay, now tau equal to Fa y bar by IB. F as it is I have written A, this area, what is this area? X into 20, right? This is 20, this is 20. Okay, then y bar is this distance. This distance is nothing but 150 by 2 half minus this 20 by 2. Okay, I is nothing but it is symmetrical about IXX, so IXX. B is this one, 20. So now we need to find IXS first. We know IXS1 plus IXS2 plus IXS3. So 1 plus 2 plus 3. I have divided it into 3 parts. As we know that first and third section are same, I can write this as 2 times IXX1 plus IXX2. IXS1 equal to IG1 plus AH1 square, IG2 plus AH2 square. Here it is BD cube by 12. For first section, B is this one, 70, D is 20. Okay, and the area is 70 to 20. And then H1 distance is this height. Okay, same as y bar, 150 by 2 minus 20 by 2. Okay, right. So again IG2, this one BD cube by 12. B is this one 10, D is 110. Okay, 150 minus 150 minus 20 minus 20. Okay, so it is 110. So BD cube by 12 plus area into 0, because neutral axis is on central axis, both are same, so 0. Y and y bar is same here. Okay, Ixs will get it as this one. Right, now substitute here, then we'll get tau. Okay, substitute, you will get tau in terms of fx into x. Let this be question number 5. Now let us find this one, tau into dA, no, s equal to tau into dA. So we will find the s values, s1 and s2. First we will find s2. Okay, now shear force in elementary area dA equal to tau dA, s equal to tau dA. Okay, to the right side, that is total shear force in the right side. Total shear force means integration. Okay, so to the right side means s2, we have taken it as s2 equal to integration tau dA. So dA is equal to first of all, what is the limits? To the right side it is 0 to 40. 0 to 40. dA is nothing but b into dx. Okay, b is nothing but 20. B is nothing but 20. dx as it is I have written. Tau already we have calculated here. 0 to 40. If I do integration, I will get s2 as this one. Let it be equation number 6. Next, shear force in the left side flange, s1 equal to integration 0 to 30. Okay, 0 to 30 left side. Tau b dx, here b same, but the limits are different. Here it is 0 to 40, here is 0 to 30. Okay, now if I solve, I get this one. Now substitute s1 values in equation number 1, E equal to s2 minus s1 130 by f. Okay, so in this way we can find the position of shear center, E equal to 4.54 mm. Otherwise, if the question is for 2 marks, we have direct formula for to calculate shear center for I section. Okay, the formula to find the shear center for I section is E equal to h square t1 b2 square minus b1 square for I section for this type of I section. Okay, h is the height of the section, that is this one h. Okay, it is not h1, only h. Okay, this is h, height of the section. B2 is a longer length of the flange. This is B2, longer length. This is shorter length, B1 shorter length. T1 is the thickness of the flange. Ixs is the amount of inertia about Ixs. So all the values we know. H 130, H is 130, 150 minus 10 minus 10. Okay, right. So here T1 is a 20, B2 40, B1 30. Ixs is already we have calculated, so substitute, you will get this one. Thank you.